Okay, all good? Hi. Okay, good morning everyone. How are you guys doing? Good? Okay. So, who remembers what we were talking yesterday? Come on. Sorry? Okay. Yes, we talked about deep learning as well. But there was one thing that I said, like, look into what exactly we are looking at. What was the AI programming? You remember that? I talked about, like, when you write an AI program, what do you do? Okay, let me give another hint. We talked about Deep Blue. IBM's Deep Blue, and then we said, what does the Deep Blue do, or how the Deep Blue was written? No idea? All right. I posted those slides back on that Google Classroom. Yeah, so make sure that you have a look at it. We're going to go a little faster today, so make sure that you do understand what's out there, because otherwise it will become slightly difficult. So what I'm going to do is that I'm going to review a little bit of what we did yesterday, which was primarily a historical kind of timeline as to what happened in artificial intelligence, or the entire area of the artificial intelligence. But this time we'll focus a little bit more on the neural networks and the generative AI, which is really the topic here, right? So feel free to ask questions, raise your hand if you have any questions and things like that. So a little bit of more specificity, but more or less the same thing that we were talking in terms of historical things. So the field itself, the AI started in 1950s, right? We talked about a Dartmouth summit or a Dartmouth meeting. We'll talk about that again here. So there were two major players, John McCarthy, Alan Turing, who were key researchers in the field. They started in somewhere around 1950s. 1956 is when the Dartmouth conference happened. 70s and 80s, a lot of work was done in expert system. We looked at example of expert systems yesterday. Schematic, not in detail, because it's no longer the area which is active research development. It's clearly understood that's not the direction the AI would go. But in 70s and 80s, 50 years ago, that was the direction, and that's where they were thinking that the AI would come from. Machine learning started in 90s. Not that every concept started in 90s. You will see that a lot of mathematics behind it is centuries old, right? It all has been there, just that we didn't know how to use it. In 90s when it started, it was very clear that statistical learning is important. That means the probabilities and statistics is going to play a role in whatever we do, right? When you do, sometimes, let's say, you want to catch a train, you say, okay, I'm getting late. I might get it, I might not get it. It's probability. It's the statistics, basically. It was very clear 40 years ago that the statistics is going to play an important role. The early work in the AI, decision tree, for example, support vector machine, any kind of regression is all statistics, right? Hopefully, most of you know it, right? And then, if you continue from that point onwards in about 2000s, the computing power became more easily available. More data could be stored in the disks or in the some kind of network where it's easily accessible. It could be put it into a LAN or a WAN. That's when they started thinking in terms of neural networks. We will go into a little bit more detail in neural network later today. The difference between a neural network and the earlier approaches was the availability of the compute power made it possible to start mimicking our brain. It's not that this was the first time that they preferred, but it was always thought of it. We need to understand how human mind work and then try to mimic it in the machine to make it a machine work the same way as the human mind work. So the thought was always there. And when we go into neural network later today, you will see that this is not something which was discovered in 2000. It was known early 50s, 60s that this is how it will become and this is how it will actually be possible. As a matter of fact, the fact that machine can learn actually goes back a couple of 100 years ago. There was someone who actually built a machine which actually showed that it can learn. Now we'll have to define what learning is. We talked about yesterday the learning starting from data, information, learning, knowledge, and intelligence, right? We'll keep coming to those things because unless we define what we mean by learning, you can't really be sure that you have achieved learning. If you don't define it, you don't know whether you've achieved it or not, right? So, what happened? Somewhere it goes. Okay. All right. So, neural network, we'll talk about neural network. Majority of the today's session or sessions, if we stop in the middle somewhere, will be focused on two things. I mean, obviously the generative AI is the focus. We'll start from the very outside. Majority of you mentioned yesterday that you've used the ChatGPT one way or the other. So if I take that's your introduction to generative AI, we'll start from there. We'll start kind of peeling off the layers of the onion and see what's inside there. We may also take the bottom-up approach where we'll say, okay, how does the brain function? Neurons, and then how the neurons lead to neural network. We'll focus a lot more today on that. Once we had gotten to the neural network, the next revolution that happened in last 20 years, 2010, is what we now know as a deep learning revolution. And this is something, okay, those words have gone here. Keep this in mind. We used a term yesterday called sentient and an emergent behavior. There was another word that we came across yesterday was latent space, right? So keep those things in mind. By the way, there will be a few more words that will come in today. Some of you may know it or may have heard about it, but these words will come in because we are trying to discover something new here, learning a new field, right? So keep those words in mind: emergent behavior, latent space, sentience, and then we'll try to figure out, did the machine learn? Is it really learning or is it really repeating? So understand one thing here. Even from the day one, when you start learning or someone starts learning, it's one thing to literally take the notes and regurgitate it out in the exam. That's not learning. That's a recall. You're storing something in memory and then putting it back. Do you want the same kind of intelligence in your machine? Remember what we talked about yesterday. The intelligence is applying a knowledge in an unknown situation. Not that somebody told you that here are the 4 points and then you go back in the exam and write down the same 4 points without realizing why, how to use it, where you can use it, etc., etc. So it's one thing to memorize. Same thing applies in the whatever machine learning we will do. We want our machines to learn, memorize, and then be able to use it in areas where they were not explicitly told to use them. That's the key difference, right? That's what the emergent behavior is and the latent space is. So we'll continue to talk about these things, and I'll point out what is leading to and why people, not why actually, how people or researchers in this field started realizing that at what point the emergent behavior actually is visible or usable. Okay, so 2010, deep learning started. Basically, what we said here is two things led to it. Large data sets, because large data sets were easily available, and also the hardware technologies, the GPUs, which were basically trying to get the certain kind of processing power available in computers, right? AlexNet was one of the implementation that used a methodology or an algorithm called backpropagation. Anyone here have heard the term backpropagation? The concept is not new. The concept was not discovered in 2010. Anyone here who has done control systems or control theory in electronics and communications? You have a feedback mechanism in control systems. So backpropagation is one way of implementing feedback system in machine learning applications. So the concept existed. It was used, and basically by using backpropagation, AlexNet was able to really solve a competition called ImageNet I think yesterday somebody was mentioning, one of the people yesterday mentioned that, and DARPA had a contest to actually have an autonomous vehicle, and that led the universities to do this. This kind of thing happens a lot in the world, that people put the prize and then give a challenge out, and there's a competition. So it doesn't matter. Basically, the LXNet was one way the deep learning was implemented, and it was realized that by having a certain amount of data, a certain amount of feedback mechanism built into it, you can actually build the deep learning systems, and those systems was going to help you implement machine learning. After that, in around 2014, 2015 timeframe, the emergence of generative models happened, what we know them today. So think of it this way. GPT or ChatGPT, as you know it, came in the scene like 2-3 years ago. In common understanding, became common. But it's been around for 10 years. Right? The Google had it. The GAN was done at Google, and the GAN was basically the generative adversarial network was one thing which basically started doing the realistic image generation, because what was possible is that they took out the human intervention away. If you think about it, it's the back propagation, which is a feedback mechanism, but what the GAN is doing is that you're having two machines. One is generating the image, second one is giving the feedback as how good or how bad it is. And then once you put this into a loop, you get the desirable output. From there, it went to the autoencoders, which is another algorithm or architecture to actually do the same kind of generative behavior, this time by doing probabilistic modeling and generation. We'll go into these things probably a couple of days later as the time comes in. And then what we have is the more development in large language models. Can someone tell me what exactly would be the more, or what's new? How things are changing? ChatGPT 1, 2, 3, and then 3.0, or whatever the case may be. And that is why I asked the question that what we were talking about it. See, if you think about it, at the end of the day, you need to keep in mind or focus what is AI programming. When you are developing an AI system, what are you trying to do? Because what you're trying to do is what you're going to improve on. So what did we say yesterday? And I'm bringing it back before we move on to something new.
A machine which solve the problem which don't have any experience.
True, but you're basically defining it, and my point is that how would you do this? All right, let's do it again, and let's keep this in mind, because there are certain things which will be throughout the session, throughout the day, or maybe beyond the day will continue. So there were a couple of things we were looking at. Goal was definitely one. There's got to be a goal. Then we said that there has to be a way to represent the knowledge. So some kind of structure which can hold the data for you, right? That's what we said that. And then we said that we need to somehow be able to generate the potential alternatives. And then we said that we need to search through and find the most optimal operation, or most optimal result, or most optimal activity or prediction, or whatever we want to call it. So if you think about it, if somebody asked you to describe in one line what is AI programming, you're doing three things. You're trying to find how to structure or store the knowledge that you have, right? That's what we said. Knowledge, when applied to an unknown situation, becomes intelligence, right? So you need to know how to keep the knowledge that you have. So that's one part. So always you would see if there is something new, some new research is happening, it will be one of these three, or maybe combination of these changes. The second thing, when I said that, is you're applying. Now, this is not deterministic. If you knew, right, you would always write an algorithm and write a program. It's no longer intelligence. It's just basically you programmed it. You know how to do the matrix multiplication. You can write a program and multiply two matrices. So the second thing is to generate the alternatives. What are the possible alternatives? And then the third thing is that how do you pick one out of many possible alternatives? We talked about the original or initial AI programming was doing A star, AO star search, which was really you organize your potential solution in a search space and you search through it. So how do you organize knowledge? How do you generate the alternative outcomes? And then how do you value those outcomes? Which one to pick or which side to go? Okay. Let me remind one more thing that I said to give this example, and why I want you to understand this, that the way I usually do is that there will always be an underlying theme. So anything we are doing today, later today, tomorrow, next week, you always think in these three things in terms. Are we improving the knowledge representation? Are we improving the generation of options? Or are we improving the choice of which option to take? That's what you're trying to do all the time. If you go back when I was talking about yesterday the Deep Blue IBM computer, right? The chess was not that difficult, just that they didn't have enough computer. What they did, they found a way to represent the state of the chessboard. The moves will generate the possible next move, and then a human was thinking 20 moves going forward. All the machine needed to do is to go beyond that. Think 21, 22, 40 moves. That's when the Deep Blue defeated the human, and now no human can defeat it, because the human mind, unless the human mind is trained to go beyond what computer can do, right? So keep this in mind. Always think in those terms, that whenever we are talking something new, what is changing? Is the knowledge representation changing? Is the generation of new option is changing, or figuring out how to find the best one? Okay, so generative models. Now, in parallel, generative model, in this we went one way, the deep learning, and then the generative model. I have not yet introduced the term neural network, right? So I'm going to now introduce the neural network. How many of you have heard neural network or have some knowledge of neural networks? Okay, what do you know?
The rudimentary understanding is that a company called Starlink has implemented neural network, and the media portrays it as something very appalling, like the likes of Transformer movie or something, an apocalyptic event.
Okay, let's leave the movies aside here. All right, fine. I'll ask this question again, maybe tomorrow. Like I asked that, somebody asked yesterday that how do we test in like in my other classes. That's one way. It's simple recall. Can you retain it for 24 hours, right? That's not the goal. That's the first step. I want you to retain at least for the 2 weeks that we are talking, because you want to link something we're going to talk about on the day 8 from what we are discussing today, because that's what is the whole idea, that you have to make sure that there is some kind of a continuity in what we are talking. It's not that randomly I'm picking topics and covering those, right? Okay, so one other thing, if you notice what I mentioned here was that, maybe it's not here today, but like yesterday, that there's always the thought process, even before 70s and 80s, that somehow we need to mimic how our brain functions, right? So the concept of a neural network actually started from making sure that how exactly the brain functions. 1958, there's a researcher named Rosenblatt who basically thought that if we can mimic how brain functions, we can teach machines to be intelligent, right? So not just that it was the electronic engineers or so-called computer scientists. Rosenblatt actually implemented not only schematically, but a machine which acted like something called perceptron. That's the term that the Rosenblatt introduced. Perceptron was based on how the human brain functions. I'll go into a little bit more detail today itself later on. Right now we're just focusing on major milestones in where we are today and how we reached here. Perceptron was the first implementation, a mechanical or electromechanical implementation of the basic unit how our brain functions, which is called neuron, right? So we'll go into the detail a little bit more, but it was a very important milestone in getting to the point where we are today. In 1986, the back propagation was the algorithm that was discovered. Now again, keep in mind, I just said a few minutes ago, it was not discovered at that time because the entire concept of feedback mechanism was known in control systems and control system theories for at least a generation before. The back propagation was the algorithm that was discovered or invented to efficiently do it in software. Okay? Let me take a little bit of a detour here. I think you were the only one who said that you know the control, the feedback mechanism. What is a feedback mechanism? If there's a management student here, you should also know the feedback mechanism, feedback system. How does a feedback function?
So whatever output signals we get, we give it back to the input signal again and then again to the whole system.
Why? Why? You always need to ask question. If you're learning something, why am I learning this, right? Why? I mean, you described it correctly, but why? So in the control systems, basically what we say that this is something which is a black box. You have an input and you have some output. The output may be, let's say it's an output achieved, output desired. It may or may not be same. What the feedback system does is that it says that tweak something here or both so that the difference between these two things get as close to zero as it can be, right? That's what is the feedback mechanism is. Right? That was not my question. That was a setup. How do you do this? So realize what I'm saying here. The feedback mechanism, and I'm jumping a little bit ahead, it's a detour a little bit ahead, we'll talk about it, but I thought I'll just mention it here. The feedback is saying that you change something, some delta needs to be applied, right? What delta needs to be applied? I think yesterday I asked a question about driving. How many of you know how to ride a bike? Okay. Do you use the feedback mechanism in bike or biking? Yes, no, maybe? Give me an example how.
How we synchronize the clutch and gear shift smoother rides.
Okay, you're going on motorbike. I'm just simply asking that regular bicycle. How do you use the feedback mechanism in there? Ignore the bike. Give me an example in your life. Have you ever used a feedback mechanism? How do you use the feedback mechanism? If you can answer me that, you will understand neural network in like 2 minutes.
We will ask someone.
Sorry?
We will ask someone who got experience.
Okay, that's supervised learning, right? That you'll ask someone, am I doing it right or not doing right? That's okay, not feedback. What's the feedback do you apply? Come on. Okay. Go back, whatever, 10 years, 15 years when you learn how to ride a bike. Did you ever fell down? Yes? How did you learn not to fall down?
Shifting of body weight and that is
Correct. So, what do you do? How do you shift the body weight?
like back testing that body. Back testing yourself.
Don't use those words. When you were learning to ride, you didn't know back testing. Right? Ignore all that thing. If you were if you were falling on the left side, you will shift the weight to the right side. That's your feedback mechanism. So what are you doing? You're saying that change in the opposite direction of what the incorrect behavior is. That's your feedback. The feedback is always negative because you're trying to correct something. If you already achieved that, the observed output is exactly what was desired, you don't need any more changes. If you need changes, they will always be in the opposite direction of what this difference is. So, let's say you were falling to this side, you shifted the weight, you shifted too much, now you're falling this side. Eventually you will learn that how to balance. That's what the feedback mechanism is. The point to note, and we'll come back to it, feedback is always negative. It's proportional to the desired output and is in the opposite direction. Because if when you're falling left, you correct it to the right. If you overcorrect, now you're falling to the right, so you again correct, and eventually you found the right balance. So what will happen is that at the point where you find the right balance, this will become 0 because you don't need any more change. You have already achieved the balance. Okay? All right, keep this in mind. We'll come back in a couple of hours to this part here. Backpropagation was an algorithm that actually implemented this in the software. What I just described, how to apply the feedback in learning how to ride a bicycle, or if you think about it in the control system theory, it will be something like it's a mechanical system which is monitoring, let's say, pressure in a valve, and it's basically if there's too much pressure, it will open up the valve a little bit. If it is too less pressure, it will close the valve a little bit. But that's what it is. Backpropagation does the same thing in software. You're writing a code to do it. Okay? So I'm not taking this detour any further, but I didn't come to my original question, but we'll come to it when we reach there. Keep this in mind. Maybe I'll ask you guys the question then. From the neural network, then we started creating multiple different kind of networks. Now, why would we do that? Same three things. You're trying to improve either representation or generation of the alternatives or finding the best alternative. Now, there may not be the best answer, right? I mean, you should know this from your computer science background. There is never a the best answer. To do the same thing, you may use a linked list, you may use a doubly linked list, you may use a stack, you may use a queue. For search, you have a binary search, Fibonacci search, sort, you have like 10 different options. Depending on your data that you have and your goal you have, you may have a different answers. So same way, once we discovered neural network, then we started discovering different types of neural networks. Why? Because we were trying to improve one of the same three things that I talked about. Why? Because the data could be different, goals could be different, expectation could be different. That's all. If you think about it, right from early 2000s, 1998, what is the research going on? Just to improve one of these three things. That's all. That's what the research is all about. So we will have a look at some of these new kind of networks, like conventional neural networks. They're like, I would say that if not 100, they're in high teens. There are like 70, 80 different well-established research papers which have variations on the neural network, because either they are improving one of these three things, or they are improving all three of these things, or they are taking one type of neural network into a different problem domain. That's what we have been doing, right? Convolutional neural network, then we have something called recurrent neural network, again trying to do a similar implementation for a different set of problem. Generative models, I mentioned the GANs and the variable autoencoders. We will look into some of these things here, right? Okay, that's where the history stops, because this we are already like 10 years ago, 2015, 2016, which is when the GANs and VAE came in the being, right? Let's now come to what you have, your understanding of generative AI, which I would presume to some confidence level, because I asked this question yesterday, is the ChatGPT is what you think is the generative system is. So this is the first time I have not defined what is a large language model yet, right? I already brought up this slide. I think I asked informally, what does ChatGPT do? So let's look at it. I'm not going that route today. Let's just get this page here. And the reason for that is there are a lot of new terms that I'm introducing here. Now, when I say I'm introducing here, I'm not introducing in the world. I'm introducing to this class today here. Some of these terms we'll continue to refer or come back to. First statement, seismic shift. Yes, people realize that AI is real. It can do something once they discovered the ChatGPT. It can do things which are real and can do things for you. What is ChatGPT, or what is a large language model, right? Now, I'm not spending too much time on it because, as I said, that we'll go on each of these words. They are probabilistic systems. I mentioned this yesterday, that 4 mathematical concepts or 4 areas of maths that you need to know. Okay. Today, I mentioned yesterday the linear algebra quite a lot, matrix multiplication. We'll come to that. The first out of 4 I'm introducing right now is the probabilistic system. Okay. Anybody who does not understand probability, let me know. If you want to understand neural networks, if you want to understand generative AI, you got to know the probability. Okay. All right. So, attempt to predict word sequences. That's all it does. Okay. If you take it a non-charitable view of what is generative AI, it's a fancy autocomplete system. You give it a prompt. Now I'm introducing a term prompt also. All of you are familiar with prompts, right? You give a prompt saying the sky is, ChatGPT will say blue, right? It's auto-completing your sentence. So a very non-charitable definition would be that all they're doing is autocomplete. That's what they do, word by word prediction in the context of your prompt. Now I've used a word here, the context, but we should all know the context is important, and we'll come to that a little bit later. Is that point clear? We'll keep coming back to this. What is large language model not? They're not fact databases. That is what separates them from AI systems like Deep Blue. Deep Blue, on the day when the IBM computer defeated Garry Kasparov, which was a world champion, was a great news, huge news. IBM spent billions of dollars on that, thinking that they would make a system that will help the doctors, the lawyers, the finance world. Never achieved anything. Why? Because those systems were fact databases. They were trying to go one better on an expert system. Expert system had the answers mapped to questions, and the understanding was that you as a user ask a question, it will search in its database, find out the answer, and tell you what the answer is. LLMs are not the fact databases. Why they are not the fact databases? Because the fact databases do not have what we said here is the latent space. Everything in a fact database is there. It's either there or not there. There's nothing new to discover. LLMs are not fact databases. They intend or aim to get this area of what's called latent space, because that's where the intelligence comes in. No one told the machine that you can do it this way, but machine finds it that it can do it this way. What they're doing is that they're statistically modeling how words tend to appear together based on their training data. You do need the training data. What do you do with the training data? You structure that data. One of these 3 problems, I said, every time you're generating or developing an AI system, you're trying to solve these 3 problems. That, and then it will statistically model. So it will generate an output based on what it knows about the world that you live in. Is that clear? Right? This was the top-down approach. I did not go word like a concept by concept and arrive at a definition. I started at a definition and then trying to give this answer to you. All right. So next few slides, we'll continue to talk about what generative AI is, LLM, and as I mentioned earlier, is that we'll take it like an onion and then try to kind of take the peels out of it and then see what's inside and how exactly it functions. Okay. So let's move on. What we do here. What else it does? Generally, it's implemented as a deep neural network and we will see the reasons today why. Okay, I'll ask those questions maybe a little bit if anybody can make a guess why it is implemented as a deep neural network. Just make a guess at some point of time. But basically, and I'm just going by like a onion approach here. Implemented as deep neural network, it's given today. I mean, and we talked about that there are multiple different types of neural network possible. We'll see that. Trained on massive amount of text data, a lot of data that has been they have been trained on, right? Why a lot of data? Because if you think about it, the approach, the difference between the Deep Blue took and this one is that in the Deep Blue, they gave all the rules to the machine. Okay? So in a theoretical way, it was prescribing all potential solutions and then only letting the computer to search through the potential solution to find the best solution. There was no learning per se. It was all that facts are given to you. The thing that the computer was doing better than the human is that searching through a larger amount of data and much quicker than a human can do. That's all it was doing. As against, here we want learning to happen. Learn the patterns of language. Learn the patterns of language, not that what the human is telling you, but just giving you the language that humans are using and say, you figure out. Okay? Unsupervised learning. That's what is going on here. Okay, let me ask the question here now. What do you think? I mentioned that the learning is happening as an unsupervised way in ChatGPT. Does ChatGPT only do unsupervised learning, or can it also do supervised learning?
Also, because sometimes when I'm searching for this, it's asking for feedback also, like it's correct or not. So it's basically trained over unsupervised learning and further tuned into supervised and second one.
Okay, who was talking here? Okay. All right, so two things actually. First of all, when you said that it's asking the question, no, the model cannot ask you question. That's number one. Tune is right. How do you do the tune? Okay. You're learning fast. Yes. So we'll come back to it. So the one word that I use, a prompt. When you give the prompt to a large language model or a ChatGPT, while you are prompting it, you can actually give it some new learning, which would be called supervised learning. So one of the things that we're going to talk about in a few minutes from now is something called prompt engineering. Has anyone heard the term before, prompt engineering? What is prompt engineering?
So it's basically generating a text in a manner that a machine can easily generate and can also convert into a specific token so that a model can easily understand and give the output based on that.
Okay, anybody else wants to take a shot on defining what prompt engineering is? Okay, all right. So basically what we are saying here in the sense that we were defining the large language models and we says that they are probabilistic systems. They are basically predicting the next word in a context. Then I said that they learn using the unsupervised learning. Then I asked you a question that can it do supervised learning? Prompt engineering is in a way the supervised learning that you are giving to the model. See, when you are interacting with ChatGPT, for example, the model already exists. The model has already learned, and that's, let me introduce another term here, that's why it's called foundation model. Because the model exists, you have no control on how model was trained, how it's working, how it's operating. But the model, or at least if you put it this way, the developers of the model allow you to provide additional knowledge in a supervised learning way. That's called prompt engineering. There's a little bit more to that, and we'll come to it when we are covering the prompt engineering. We'll cover in the next few minutes, actually, in a way. So, the model, the base model or the foundation model is usually trained in a non-supervised or unsupervised learning. It helps it to do a lot of tasks which were traditionally part of natural language processing or NLP. If some of you may have learned the NLP basically, right? So in general, the large language models were designed to predict the next word in the context provided by you, user, based on the learning that it has already done or knowledge that it already has. Now, once it has done this, it can do a lot of different tasks called machine translation, text generation, question answering, summarization. We're going to actually spend a few minutes, I'm not sure the order, but like a few minutes in looking at the various use cases of the large language model before we go into the deep. As I said that we'll take the onion approach in the sense that what can you do, and then we'll start learning how is it happening before we actually go to the next step saying that how can we actually program it or change it or do something with it. Okay? Very powerful, but still need guidance. And this guidance is the supervised learning that I just talked about. The model is very powerful, right? How many of you have heard the story of Ramayana? Right? And the character of Hanuman? Right? Is there a parallel between what I just said and Hanuman? What? Not exactly. So the story goes that the Hanuman is all powerful, right? But he is not aware of his strength, right? And there's a character named Jamwant who actually reminds Hanuman that yes, you can do that. So Hanuman had innate unsupervised learning, but he was to be told you can do it before he goes and does it, right? That's what we're saying, that they're very powerful, but they still need guidance to unleash their full potential. That's what the prompt engineering do. The prompt engineering is basically the set of skills that let you as a prompt engineer to make the best use of the model. When you are interacting as a prompt engineer, you're not changing the model. You are augmenting the model by giving it more guidance, supervised learning, specific to your prompt. All right, we'll come back to it. So when you are using it, so I'm differentiating between a researcher, a developer who actually developed the model, and there are users. A prompt engineer is really if you think in terms of, I don't know, customer support engineer or whatever the case may be, closest to the use case. Because you're not changing the model, you're augmenting the model with the desired output that you need. Other than prompt engineering, or actually as part of prompt engineering, there's also something called sampling techniques. Now, sampling is a word which also comes from statistics. Okay? Keep in mind, there are terms that will come in which relates to probability and statistics. So make sure that if you have any confusion in those terms, ask the question. Please raise your hand. I mean, in the worst case, as I mentioned yesterday, I would either defer it or refer to you something else or answer it in the best case scenario. So, sampling techniques relate to how do you want the probabilistic component of the LLM to behave. Is that clear? Yes, no, maybe? All right, what is probability? I mean, if you don't understand this part here, it will start getting confusing going forward. So I just want you to make sure that you understand this. What is probability?
The likelihood of an event occurring.
Likelihood of an event occurring. Is it discrete or continuous?
It can be discrete and continuous.
It can be discrete and continuous both at the same time?
No. Actually, discrete we are assuming, but it's really it is continuous.
Okay. Is that 100% true?
No.
No. Your statement that we are assuming it continuous.
It's also a problem.
So rolling a dice, is it a continuous or discrete, or is it continuous, you are assuming it discrete?
If you have some number like we need to go at 5 times, then it's a particular.
Can you roll a dice and get a 3.5? Okay. So it's not that always continuous and you're treating as discrete. It all depends on the sample space. If the event that you're monitoring is rolling a dice, the sample space is discrete. So the probability of having a specific output is a discrete number. It's not continuous. But in real life, not every event is discrete. So you're partially right, and I'll go back to and remind you something else, especially important if you are doing research, but also if you're trying to get a job, you have to be very specific of what you are answering. So you may be saying 100% correct, but it is not relevant in the context that the question was asked. You understand what I'm saying? All that you said was all correct, except that you were missing out the point, the question of sample space or the event space. If the event that you are modeling are discrete, then probability is discrete, otherwise it's continuous. Because you cannot model a continuously occurring phenomena easily, you model it by using discrete methods. That happens. Make sense? Okay, let's continue on the continuous part of it. How do you model continuous probability? PDF? Anyone heard of PDF? Probability distribution function. Sorry? So, if we were monitoring the roll of a dice, right? You will have probabilities like this. 0, 1, 2, 3, 4, and 5, and 6. Actually, there's no 0. 1 to 6. You have discrete distribution of probability. If you have a continuous distribution of probability, the graph will look like this. What is this called? Sorry? Bell curve, normal curve, but what is the distribution called? Normal distribution, right? Now that is basically a function that is used as a probability distribution function in a way, right? Now it's a probability distribution function that has been observed in lot of natural occurring behaviors, right? So what is probability distribution function is doing? The probability distribution function is telling you that if you observe a certain event space for a sufficient number of time, this is the kind of behavior you will observe, which says that majority of the time you will find that events are occurring in this space. As you go towards the tail, now this is just one distribution. There are infinite number of distributions that can happen in the event space that you are observing or modeling. Is that clear? As I said that the large language model is a probabilistic system, which means that there's got to be a probability distribution function underlying the LLM systems. If you are trying to tell the model that how should it pick the answer, think of it, it's a probabilistic, which means it is picking up an answer based on some probability somewhere. If you want to control, you can change what is known as sampling techniques. Now what is sampling technique? That whether you want to pick a sample from this space or this space or this space. What's the difference? If you pick from this space, it's basically you're picking the most common possible answer. Otherwise, if you're picking in the other side. Let me introduce one more term, or actually ask you one more term. What's a cumulative distribution function, or CDF? Any idea? So, let's say if you are rolling the dice, what's the probability that you get a 1? One by 6, right? What's the probability of that you get a 2? 1 by 6. What's the probability, 1 by 6. What's the probability that you get either 1 or 2? Right. So you're basically saying that you can either get this. So if you draw a probability distribution function of these, it will be like this, because there are equal probability of getting every of these discrete values. But if you draw the cumulative distribution, it will look like this. Because probability of getting 1 is 1 by 6, 2, either 1 or 2. The cumulative probability is 2 by 6. And if you say that, what's the probability of getting either 1, 2, 3, 4, 5, or 6? 100%, because you're going to get one of those. So cumulative distribution function for a probability function is that it's basically giving you up to that point, what's the probability. Is that clear? We're going to come back to these things when we are going to discuss about sampling techniques. And why we are discussing sampling techniques? Because as a prompt engineer, if you're trying to get full potential of the underlying model, those are the tools available to you, right? So I mentioned 2 tools here. Which ones were the 2? Recall question. as a prompt engineer, you do provide supervised learning to the model, and then you basically tweak the sampling parameters that are available to you. So, and what are these sampling parameters? Telling model where in this probability space it should pick its answer from. What is picking the answer? Go back to the same three things we talked about: representation of knowledge, generation of the alternatives, and picking up the right answer. By tweaking the sampling parameters, you are basically instructing model to pick which answer. At any given point of time, the model may have 200 possible answers. Which one should it pick? Right? That's what you control using those sampling techniques. All basic mathematics, nothing beyond that up until now, right? Okay. Is this point clear? Okay. All right, let's move on here. So, I think I've already covered this in the sense that how do you make use of the model? A lot depends on how you control the sampling parameters and the prompt engineering that you do. And that's what we're going to cover in the next few minutes, basically. So let's continue on the sampling techniques, basically, right? So what is the sampling technique doing? And keep in mind, most of the information that is going to come here, we have already talked about it. So I mentioned that it's a search that is happening. All AI programs are always doing some kind of search. The default behavior of a model, and especially ChatGPT, is the greedy search. Now again, keep those words that we talked about yesterday, greed and gossip, right? The greed is not always bad. The greed is possibly the best thing if you want. So the default behavior is the greedy search. There's a class of algorithms that if you have taken a data structure or an algorithms course, is the greedy algorithms, right? Optimizing whatever is the cost function, or minimizing the cost function, or optimizing the benefits. That's what the greedy probability. Now, what's the disadvantage of using? I mean, this is the best possible, because you're picking up, or you're instructing the model to pick up the most probable answer at every point of time, right? Because that's what your greedy algorithm is trained to do. Take the best path, take the best option, right? And that's the default behavior generally. Is that good? Why? Sorry?
So similar answers among all the users.
Right. So what happens is that if everybody is so, it's good in many cases. If you're trying to find out 2 plus 2, it should always answer you 4, right? But not necessarily in text generation the way you wanted it to do this, because if everybody gets the same answer, right, you won't be able to cheat. We will know that you all have used the same prompt and it has generated the same answer, right? So that's the greedy search. But generally, if you let the model to act like this, it will usually give you a repetitive and predictive answer, which is many times is a desirable attribute because you want a deterministic answers. But that's not what we are looking into a large language model, right? We're trying to mimic human behavior. In human behavior, we're not all same. We are all different. I mean, even if the same input goes through us, we all receive it differently, we all process it differently, we all store it differently, and we all process or retrieve it differently as well, right? Okay, so this is one way. What could be the option if, let's say, you say, we don't want greedy search, we don't want the predictability, we don't want the deterministic answers. What's the other way of doing it? Sorry? Let me invoke another little bit of maths here. Not that important for this, so I didn't mention it in the last 4 thing. Queuing theory. How many of you have studied queuing theory? What is queuing theory? No? Come on. How is that possible? If I studied in this college queuing theory 40 years ago, well, how come you guys are not doing it? Anybody who did operating systems course? They didn't cover queuing theory there?
People are standing into waiting for their service, just like a patient waiting in service.
Yes, that's one scenario, but that's what it is actually. The queuing theory is study of the queuing behavior. Queuing behavior means there are a lot of people who are waiting for a service to be done, and then there are fewer people who are providing those services. How do you manage that? That's called queuing theory. That's an entire way of figuring out. Okay, when you implement a queuing theory system, I'm okay to go take a little bit of a detour, but please ask the questions if you don't understand, right? And one other thing, and I'll emphasize it again, if you are doing research and if you are trying to do the research, this is all you need to do, is to find connections. Because if you just go straight line, keep looking at, you will never discover anything new, because you're only going to find that somebody else has already found it. In research, you're always looking sideways and trying to find the relationships or connections, right? Okay. And the reason why I went to queuing theory, and I'll come back to it, in the sense that I said that if the greedy search is not what we are looking for, what alternatives do we have? What else can we think of? And from there I went to asking about the queuing theory, because what happens, what's your name? Neeraj. So Neeraj gave an example of people are waiting in hospital, right? I mean, there are, everywhere you'll find the example of queues. When you study the queuing behavior, what you do is that, let's just take a minute or two here. There are a couple of different things. There are service providers, those who are providing the service, and there are service seekers, those who are getting the services. The service seekers come at a random interval. You don't know. They may be coming in burst, right? So think of it this way. You're trying to figure out the behavior of a queue in a cafeteria downstairs. Generally, you would say that people arrive at random times. Yes, but not so true. People arrive at the time when the classes end, in between the classes. So you get the random behavior arrival, but in bursts. So when you are studying the queuing behavior of a specific situation, you model the event, and the event here is arrival of a new service seeker by using a probability distribution. When you are again checking, because you do not want, when you are studying the queuing behavior, you do not want a deterministic methodology to be used, because the people arriving randomly, you want the probability distribution with a random sampling. So a long way for me to reach where I wanted you to give me the answer. If we do not want repetitive and predictable output, what do we want? Random sampling, right? So if you do not want your LLM to give the same answer all the time, you tell it to do random sampling. So rather than picking the highest probability answer, you say randomly sample, because I want variation. I want the answers which are not predictive or exactly same. Does that make sense? You find the connection between the two things? Okay, let me ask the question just so that you remember this. Hopefully you remember this. Okay, how do you apply queuing theory to an elevator? Anyone? Okay. All right. Another question. If there are 3 service providers, should there be 3 queues or a single queue serving all 3 providers? You're going to railway reservation counter. Nowadays we don't. We do it online. Let's say there were 3 counters. Number 1, 2, and 3. Should there be 3 separate lines like this, or should there be 1 line feeding to whichever is available the next? All of these problems are part of queuing theory. 3 separate lines? How many of you think 3 separate lines? Okay. All right. Now let me give the scientific answer. It depends. It depends on the context. So here's what happens. What are you trying to optimize? Are you trying to optimize the throughput of each individual of these clerks? Or you're trying to maximize the combined throughput of all 3? Are you trying to minimize the wait time for each individual? Are you maximizing the number of people served? Because the answer depends on all of these. Depending on what your goal is, the answer could be different. All right? I'm not going into the queuing theory. That's all a different aspect of it. The reason I asked the operating system question is when you are doing the process management, when you are doing the scheduling is again a queuing theory problem. If you have 5 processors and 15 processes, which process do you pick next to run? That's a queuing theory problem. Okay? All right, we're not going too much in the detail there. Now let's come back here to the neural networks. The random sampling is another choice when you are not, when you don't want the deterministic answers. Is that a good option? What can go wrong if you choose random sampling? Sorry? Correct. I mean, let's not call it error, let's say incorrect. Now, you can say that I'm splitting the hair, but we are all scientists, so we need to use the formal term, specific terms, right? So if you're telling it to use the random sampling, what can happen? I gave you an example of a prompt, the sky is, right? If it goes through the greedy methodology or greedy sampling, it will say that, hey, 9 out of 10 times I've seen in my training data that sky is blue, so it will say sky is blue. If you ask it to do sampling, maybe you will get an answer, sky is yellow, because it says that I'm asked to take a random sample, so I'll pick a random sample, right? So it's a good alternative, maybe not what you want. Okay? So now let me pose a research problem. It's not a research problem today, but let's assume that you're trying to solve it. We're not happy with the greedy sampling. We're not happy with the random sampling. What choices do we have? At some point of time, let's say 30 years ago, that was a research topic. What do? We're not happy with option A. We're not happy with option B. Find something else. Sorry? How else can you find the next best option?
Harness data from both the options and chisel them into refine them into a new.
How? But that was my question.
Sir, if we reduce the randomness, somewhere it can be possible.
Yes. I mean, that's a good way of thinking about it. We don't want the deterministicness, but we don't want total randomness. We want some randomness. So if we can control the randomness, maybe we can get somewhere the best of both worlds. Variety, but not total. It does not necessarily say that you will not get the answer like sky is yellow. You may still get it, but you will possibly, your goal is to reduce the, okay, I'm not going to use the wrong. See, when you use the word wrong or right, you're taking a position. Right? I'm saying that implausible answers. We are always talking in probabilistic space. There is no definitive things here. It's all probability, right? What you're doing is that by reducing the randomness of the sampling, you're saying that potentially I might have a higher probability of a reasonable answer rather than a completely ludicrous answer. Make sense? Okay. How you do that? How does the model allow you to do that? There's something called temperature. That's a parameter usually exposed by all the models out there. What this says, higher temperature promote diversity, which means the randomness. The lower temperature favor the high probability token. Temperature of 0 is a deterministic answer, single answer. So basically the model gives you a temperature sampling which tells you how you can control the randomness of the answers it's picking. Okay, that's not the only one way. There are slightly other models called top K sampling, top P sampling, best of N sampling. I'm not going into too much detail, but I'll just give you some answers. Based on whatever we talked about here, you should be able to understand this. So the top K sample says that, take the example of these three things here. So This is not a great example for this because the probability of each of these answers is exactly same. But assume that if there were 20 events and all of them had different probability, top K sampling says that pick one from top K, whatever the K, top 3, top 4, top 5. So what you're doing here is that you're introducing the randomness, but you're saying that pick from top 5 high probability choices. So top K is a number of choices. Top P sampling. The top P sampling says that the cumulative probability, what I mentioned here is that the cumulative density function. So it says that pick the top P cumulative probability. So it says that I want to pick you up from the sample which has the highest 50% probability. Now it's possible that highest 50% means only 3 choices out of 300. So it'll pick you that. So that's another way of controlling the randomness while avoiding the deterministic answers. Best of n sampling, which is something that you mentioned that you chisel the answers by combining together. So it says that you basically use the n different responses and some predetermined metric, whatever the metric is, that you pick that best of n sampling. These are not the only ways. You can figure out a lot of different possibilities. If you are generating, or if you are writing, if some of you go into becoming a prompt engineer, or some of you go become an LLM developer, not the user like you're just typing the prompt, but you're developing a system, whether it's a chatbot or something else, where you are trying to modify the model behavior. These are some examples, but basically you're trying to find the right way for your use case and then figure out what exactly is the best way for you to instruct the model and get the right information out. Is that point clear? Okay. So what we are going to do is have a quick look at some of the use cases of these large language models. I'm sure you guys are familiar with many of them, right? But let me take a quick view here. So next 6 or 7 or 8 slides are pretty dense. I'm not going to spend a lot of time on it, but just my intent here is just to give you a feel of where these large language models or the generative AI systems are used nowadays or today. Okay, so most common one, they are being used as the code assistant, right? They can write code, they can assist you in writing code. There are multiple different ways. Code generation, code completion. They are basically word completion systems. They can do the refactoring for you. They can debug the code. They can translate the code. You give them a Python code and ask them to write a Java code. The models can do it today. They can generate the test cases for you based on the code given to them. They can document it. They can summarize the code. Let's say you get the code written in Algol. You've never studied it. You can give it to a ChatGPT-like system, not a ChatGPT because it's not specialized for that, but there are systems which can do it and it can summarize what that Algol program is doing, right? Machine translation, instant messaging app. Basically, it can, let's say you are in France, you don't know French. You write something in English, it can give you the French translation. They can do the e-commerce. Product description is automatically translated. You can also see the feedbacks, and when you are writing ratings, they can be translated from one language to the other one. Travel apps, Google Translate, if you have gone in countries where English is not spoken, majority of the Europe fits in that, Google Translate works really well. You can scan something written in Japanese and it can tell you in English what exactly it is. All of these are basically the same kind of models. Text summarization, news aggregator. These models can do the summarization. You give it a document of 20 pages, it will summarize you for 1 page or half a page, or you can ask it to write in the bullet points. It can do that as well. Research databases, there are systems now. Now, keep in mind, the base model is same. When I say that you could be an LLM developer, you could be developing a news aggregator or a research database summarizer. The underlying model is same. You are programming it or telling it by doing the same thing, prompting techniques, the supervised learning, and to some extent the sampling, the tweaking of the sampling parameters to get the desired results, right? If you continue on that, the question answering, the virtual assistants, customer support, there are academic platforms like Wolfram Alpha, lot of these things which can basically answer the question. I ask you a question, say for example that what is a cumulative density function? You can ask that. Now, it's not that this is new. Google search was doing something similar. But keep in mind, the Google search was a fact database. I mean, what we call Google search is actually a massive sort operation. That's some other conversation. Chatbots. You can basically take the... how many of you have interacted with the chatbots of late? Sorry? Okay. So the earlier chatbot implementation were more like a decision tree. So you call a phone number, they say, oh, you want to, do you want to talk about a checking account or a saving account, or do you want to have a credit card issue? So literally what was happening, the original implementations were like a massive tree, and at each node you take a path and then eventually it will lead you somewhere. Even today, most of the systems are written that way. But if you are using a large language model behind the scene, you can make a more human-like intervention, human-like conversation. Sentiment, context, humor, it can understand all of these things, right? Those are some of the usages. Content generation. You take the question paper, give it to ChatGPT, it will give you the answer, right? Can do script writing, it can do all kinds of content generation. When I say content generation, it need not be just the text. It can generate the images, it can generate the audio. Nowadays, it can even generate the videos. A couple of minutes worth of video, not the full length movie yet, but maybe that will happen as well, right? Natural language interference, sentiment analysis. Have you heard the sentiment analysis? Right? So from the natural language, whether it's written, verbal, it is trying to figuring out whether the person who's speaking, is it positive, negative, feelings, emotions, trying to discover, is the person angry, is the person frustrated. All of that can be done by the sentiment analysis. Legal document review, medical diagnosis. This is a very active area of research. Not necessarily somewhere where people can start using it or start relying on it, but giving the entire medical history of a patient, the models are now being trained to figure out the diagnosis, to figure out what could be going wrong with the people, with the person. Text classification. This was the early uses. Spam detection, news categorization, feedback sorting, all kinds of things. Now, spam detection this is not the only way people were using it, but one of the ways it's being done here. It's going to come back, right? Yeah.
When we were doing the post questions here, then how you feeling, because that time
Sorry, say it again, I missed it.
there was no internet and there was no Java, there was no when we were doing study,
Yeah.
that time no internet, no Java, there was no Linux. In that, after that it got invented.
Yes.
How mechanism difficult of following that time? That I just want to understand. It was very difficult to understand. System was not possible. If system means if someone have PC, it does mean right on helicopter. We have a helicopter, right? That time, 1987 something.
Okay. I'm not sure I'm following 100% your question, but if you want to know about our experience, I can tell you that in general. You're talking about the internet. At that time, there was no computer. There was no computer in this college. There was no computer. 90% of my class did not even touch the computer when they pass out after 3 years here. Okay, that's a good question. The first language we were taught was Pascal. I don't know if you guys have heard of it. Yeah. One of the instructor, I don't know if any of you, a couple of you may see, he was here yesterday. We just called him and so he came by. Professor A.K. Mishra. He was the first person who taught the programming language to our class, basically. So Pascal was the first one, COBOL was the second one, and Fortran. Those were the languages.
That time operating system, Unix or
Some variation of the Unix. The one computer that this college had at that time was from Uptron. How many of you heard a company named Uptron? It was right here in Govindpuri. So they had a system and they had their own operating system. It had a memory of 64 kilobyte. That's all. Right?
one more thing.
Yes.
How did at that time, how did you feel when internet came in 1991, 1982, that time? How did you feel that?
So, okay. I mean, I think I was somewhat lucky in that perspective. I started using internet before internet, actually, before it was called UUNet. I mean, the networking was there for quite some time. Internet is a more recent phenomena, but the networking existed before that. There were tools which were, World Wide Web did not exist, but the networks were there. There were other things. There used to be things called Gopher. I don't know if any of you have heard of it. The first browser that was written, and I also happened to use it, was called Lynx, Lynx, Lynx. It was a text-based browser. So, I mean, it's a different way of doing things in the sense that internet was not there, TCP/IP was not very popular. The communication protocol which was used, which was designed by a committee, was X.25. It was a store forward network. If I wanted to send an email, I needed to know the path by which the mail would go. So if I needed to send an email to someone in Berkeley, I needed to know how do I send a packet from here to Berkeley. So I would say that from here to DOE to DARPA to Oxford to Cambridge to Berkeley, I need to specify the entire path. That's how. The Aloha was the precursor of internet. The Aloha was designed using TCP/IP, but the networks existed before that. So if you think about it, it was an opportunity like this. If you think about it, I joined a place called NIC, National Informatics Center. I got an opportunity. A couple of you here were working on the GIS or remote sensing. I worked on those topics 30 years ago. So there was a professor who came here. His name was Hanan Samet. His area of specialization was hierarchical databases. I don't know if any of you have worked on hierarchical data structures. KD tree. Anyone familiar with KD tree? I asked the trees yesterday. All right, that's fine. I mean, you don't need to, but if you are using any of this spatial computing, GIS or any of those kind of things, KD tree was the structure that was actually designed by Hanan Samet. So I happened to meet in a similar setting, not exactly the same setting. It was a group of us, and I got fairly fortunate because I was like 4 years out of the college, and this was a group of people mostly from ISRO, NASA, Space Application Center, because we were all dealing with the same remote sensing data and the geographic data. So we invited Hanan Samet. We means Government of India invited Hanan Samet. And I got an opportunity to get in touch with him. And apart from what he was teaching, which is hierarchical data structure KD tree, I personally learned how the UUNet works, what is Lynx, what is Gopher, and how do I get connected with all of these things. So anyway, these things happen, which is what I encouraged all of you yesterday, that ask questions, and this is a good question to ask, and get the opportunities whatever you get. And also, don't think always in straight line. Keep an eye a little bit on the sideways, because that's where the best of the learning. We will come to more about it in a way. Give me 1 second. Yes, sir. Okay, I'll take this off. Okay. All right, I'm told to take a stop now. Are you guys all done? You want to take a stop a little bit? I think there's a T there as well. All right, so let me just take 2 more slides here, just finish this topic and then we'll come. So multimodal applications, the text analysis, market research, we're just looking at the examples actually. More multimodal. Right, stop here. Q&A. These slides will be available to you. Okay, so why don't we take a break? I think there's a tea break down there. We will meet in a few minutes and then we will spend the rest of the time talking about prompt engineering. Okay? All right.